introduce our next speaker. So she's Birgit Rudloff from Princeton University. So she's assistant professor in Princeton, and we'll talk about convex hedging in incomplete markets.
Thank you very much. I'm very glad to be in Germany back. So today I want to speak about hedging in incomplete markets when we use a convex risk measure. And yeah, I will begin with introducing the problem and to explain what I will do. Then I will show that the dynamic problem of convex hedging can be split into a static problem and a representation problem. And then we'll try to solve the static problem. And because the conference is also together with the Center of Applied Statistics, I thought I can a little bit point out the connection between the problem and the problem of testing hypothesis. And then I will give optimality conditions for the static optimization problem. But first, to show what the problem is. So we know that in a complete market, we can always perfectly replicate a claim. So if we have a random payoff at time capital T, we will always find an admissible strategy such that the replicating portfolio at time capital T will perfectly match the payoff of the option. So we have a replicating portfolio with initial capital and a hedging strategy. And we know that in the complete market, the price of the option is the expectation of the claim with respect to the equivalent martingale measure, which is unique. But we also know that the complete financial market is restricted to such to some specific models like Scholes model. So in general, as soon as the models get a little bit more complicated, we have to deal with the incomplete market. And in the incomplete market, first of all, the equivalent martingale measure is no longer unique. So we have a whole set, infinitely many equivalent martingale measures. In general, the set will be the sigma martingale measures. But if you're not familiar with this, just imagine a set of equivalent martingale measures. We also know that not every contingent claim is attainable, which especially means that this equality is in general not satisfied. And this is why in the incomplete market, we will try to minimize the risk of the shortfall, which means we look at the cases when our replicating portfolio is less than the claim, the payoff of the claim we want to hedge. And we want to minimize the risk of this event. So we look at the difference between the claim and the replicating portfolio. We look at the positive part, which means that we just look at the cases where we are below the claim, and the cases where we are above. This is not really bad, so we have earned more money with replication. So we look at the positive part of this difference. And the minus sign in front is just because it's losses that are due when I'm below the claim. Now there are different possibilities what kind of risk measures can be used to consider when this problem is considered. And there are also already in Berlin, there were some years ago from Filmer and Leukert, there were two papers about the case when you just minimize the probability of this event, or another paper was where an expected loss function was used as a risk measure. In our case, we will consider a convex risk measure as to measure the risk of the shortfall. So just to review the setting, so H was the payoff of, for example, an option. In general, it's a non-negative FT measurable random variable. We have Vt as the final value of our replicating portfolio. And we consider admissible strategies, so initial capital and a hedging strategy. And admissible just means it's self-financing and the value process is always non-negative. And the underlying process can be an d-dimensional semi-martingale. So it's very general, can be any jump diffusion, Levy process, or stochastic volatility model. So something that in general will lead to an incomplete market. And as I said, as a risk measure, we use a convex risk measure, and I will, on the next slide, a little bit review what this means. But in general, our problem will be to look for hedging strategies that minimize the risk of the shortfall. So this is what we want to consider. And we have also a capital constraint, because you can imagine if you use enough money, you can totally get rid of this shortfall risk. And so U0 will be the super hedging price. So this is the smallest money such that you are on the safe side. But it's well known that the super hedging price is in general too high to be really a price on a tradable market. So we take the super hedging price as the boundary, and we will fix some value strictly below the super hedging price, and we will just allow initial capital that is less or equal than our capital boundary. Okay, so this is a problem we want to consider. It's of course a dynamic problem because we are looking for a time-dependent hedging strategy. And as a first result, yes? I mean, this is just a given amount of money you start with. So you take some capital, you are... in the expression, I just start with any initial capital that is less or equal than the boundary we have fixed at the beginning. So we fix a boundary and we say, okay, if we need less capital, then it's okay, but maximal money we want to use is V0 tilde. Okay, then just to review the notation of convex risk measures. So we're working on L1 because we assumed also that our payoff is an element in L1 plus. So we have risk measures on L1. And any functional that satisfy these three properties, monotonicity, translation property, and convexity, will be called a convex risk measure. I think you're all a little bit familiar with this notation. And it is also well known that for lower semi-continuous convex risk measures, we have a dual representation. So we can write this functional to be the supremum of the expected loss, where the expected loss is reduced by a certain penalty term, which depends on the probability measure Q. And we take the supremum with respect to all probability measures that are absolutely continuous with respect to the original measure we started with and have a density in L infinity. And L infinity is here because we start with a risk measure on L1. So this is just the elements from the dual space. And the penalty term is it's a support function with respect to the acceptances of the risk measure. Okay, so these dual representations are well known and we'll just use it later. Okay, so the first result will be that this dynamic problem can be split into a static problem and a representation problem, which is similar to the case that Vollmont-Leuker had for those different kind of risk measures. So we get the same thing here. We have an equivalence between the dynamic optimization problem and solving first a static problem. So this is static because we are just minimizing about with respect to random variables, so they are no longer the time dependence. And these random variables will be randomized tests. That means they just map from omega to the interval 0, 1. And they have to satisfy a certain additional condition that I will explain shortly. So now imagine you can solve this static problem and you can get the optimal randomized test. And then the second problem, the representation problem, will be to yeah, if you multiply the solution of the static problem to the claim, the original claim, you get something like a modified claim. And yeah, we need the super hedging price or the super hedging strategy of this modified claim. And it can be shown that, yeah, our capital boundary together with the super hedging strategy of this modified claim will solve our dynamic problem. So instead of solving the dynamic problem directly, we first try to solve the static problem. The solution of the static problem is multiplied with the original claim. We super hedge this new claim and get the optimal strategy for our dynamic problem. So, and I wanted to say one word more about this restriction here. It just means that all the modified claims I consider, they should satisfy that the super hedging price of this modified claim is less or equal than our capital boundary. So this is just the interpretation of this constraint. Okay, and yeah, since for the super hedging price there are already results, we will concentrate on finding the solution to the static problem. Okay, first remark about the static problem. So I've written down it again here. So this was a objective function, and we had this constraint that the super hedging price of this modified claim is less or equal than the capital boundary. And we can also use the dual representation for this risk measure if we have a lower semi-continuous risk measure on L1. Patrick?
Why do you have an X there instead of the C?
Because I can show that the supremum is attained. So this will be a result from the duality, which I will show. So after showing that strong duality is satisfied, we can show that there exists a saddle point, and then it follows that the sup is really attained here. Okay, so, but as a first remark, I wanted to show the connection to testing hypothesis. So just, yeah, if you consider the problem that you have a family of probability measures P, the null hypothesis, and you want to test it against yeah, set of probability measures Q. And in testing hypothesis, this means that yeah, you want to minimize the order, the error of second order, and which also means that you maximize the power of the test, and because we have a compound hypothesis, we maximize the smallest power of the test. So this will be the power of the test, the smallest power of the test, and we maximize the smallest power of the test. While at the same time, we want to get the first order error still bounded by alpha, and yeah, because of compound hypothesis, in this case, the largest error of first order should still be less or equal than some significance level in the interval 0, 1. And I yeah, will show you that the problems are quite similar. So, I mean, this supremum you can write as minus infimum of minus, expectation of minus phi. And then you see already that there's a strong connection to this problem here. So we are also looking for the infimum with respect to the randomized test. And here we yeah, have the maximum over some set of Q. And in the case of testing compound hypothesis, we don't have, you see, we don't have the penalty term here, which just means that this, yeah, this is something like a coherent risk measure, right? With respect to, or which has in the dual representation exactly the set of probability measures we have given in our alternative hypothesis. So, and okay, you see the difference maybe in this part here, but you can write this as an operator A phi times yeah, a random variable B, so something like this. And yeah, in the case of convex hedging, H or A, the operator A is just the claim H, and also the constant is equal to the claim H. And in the case of testing hypothesis, we have an identical operator here, and b is equal to the 0 random variable. So I just wanted to show you the connection between these two problems. And also, yeah, the constraint is quite similar. Instead of our capital boundary, we have, by testing hypothesis, we have the significance level here. But otherwise, the problems are from a similar structure, so just as a side mark. And now we want to look on how to solve this static problem. And okay, as I already mentioned, the assumption is rho is a convex risk measure. It should be lower semi-continuous to have the dual representation, and we also need continuity in at least one point. So if you consider finite values for a risk measure, they are continuous in every point. Okay, so our static problem with the use of the dual representation looks like this. And I will first give you a short overview how the problem can be solved, and then we can go into a little bit more in the details. So the first step will be to deduce the dual problem with Fairchild duality. And you see that the dual problem, it has the same objective function here, and just the min-max turns into a max-min. And yeah, this is very helpful because it makes it possible to go one step further. So also we can of course show that strong duality is satisfied, which means the primal problem has the same value as a dual problem, and we get the existence of a primal and dual solution. And also because of strong duality, it follows what you have just asked me, that also you can show that the max here and the min here are really attained. Yes?
If you assume that at one point when the risk measure is continuous, then the risk measure will be real value and will
Yes.
be continuous.
Yes, it's true. Okay. So the first step, as I said, we can prove that the min-max can be changed. And then we want, in the second step, to consider the inner problem of the dual problem. So we can fix one of these measure Q and just consider the inner problem for one specific Q. And we try to solve this problem. So this will be the second step, to go to the inner problem of the dual problem for one fixed Q. And we can show that you get some results about the structure of the solution. So we get some necessary and sufficient optimality conditions. And then with this result, it will also be possible to solve the whole problem. But I will now talk a little bit more about how to solve this inner problem. Okay, so this is a problem again, the inner problem of the dual problem for a fixed Q. And it's also connected to test theory. And in fact, this problem itself is like a generalized test problem. Because so this is the same problem, just written down the constraint again. That the superhedging price of this modified claim is less or equal than the capital boundary. And we could rewrite this problem if we define two measures, O and O star, just by taking the Radon-Nikodym derivative equal to H. And then this problem here just turns into a kind of a generalized test problem. So we just use the density here to replace Q by O, and to replace P star by O star. But now these two measures are no longer probability measures, but measures. And also our capital boundary is not in 0, 1, so it's not like a significance level, but it's a positive real number. So the whole problem is something like a generalized test problem, because you have just measures, no probability measures, and you have a little bit more general significance level. So yes, of course there are already results about testing hypotheses. For example, by Witting, he showed some necessary conditions, we will prove here that some necessary and sufficient optimality conditions which come also from strong reality. Okay, I give you first the result, and then I will talk a little bit about how it can be proved. So this is again the inner problem of the dual problem, and we can deduce with Fenchel duality the dual problem of this problem. Here the infimum is now taken with respect to finite measures on the set of equivalent martingale measures. And so here you see the densities of the probability of the equivalent probability measures appear, and the dual variable is are the lambdas. And we can show that necessary and sufficient for optimality is probably as it was expected, is related to test theory. So the result is of course also like a Neyman-Pearson test. So we get an optimal randomized test that takes a value 1 on a certain set, so on a subset of omega, and it takes a value 0 on a certain set, and we have a third condition, and the third condition determines the value on the remaining set, so where we have equality here. So it will be a random variable between 0 and 1. So we have these 3 conditions for the optimal solution, and you see that so the optimal solution depends, of course, on the solution to the dual problem. So it's a structural result, and if you can get the dual solution explicitly, it would be an explicit solution, but in general, it's like a structural result, depending on the dual solution. Okay, some remarks about the proof, and by the way, the last condition here, it just means that the superhedging price really attains the capital boundary. Okay, so the proof is again an application of Fenchel duality. So in general, the Fenchel Fenchel-Rockefeller dual theorem tells us that if we have a primal problem of this form, so we have a function f and a function g, so normally the g will model the constraint, and then we can write down the dual problem, as the dual problem now involves conjugate functions, and also we have here the linear continuous operator, and we need the adjoint operator. So we can write down this dual problem, and to get a result of strong duality, we need some assumptions for the functions. So f and g have to be convex functions, and one needs a kind of regularization condition to get strong duality. And strong duality always means that the value of the primal problem is equal to the value of the dual problem, and that the supremum here is attained, so that we have a dual solution. And one typical example of a regularization condition is that we need a point in the domain of the function f such that the function g is continuous at this point. So you see also why I needed the assumption on the risk measure to be continuous in at least one point. It's exactly the reason lies in the regularization condition. But this condition is sometimes a little bit too strong. So there exist weaker conditions which are, but in generally a little bit harder to describe. Okay, in our case, our problem looked like this. So this was the inner problem of the dual problem with a randomized test. And first, you have to get the problem in the form of the Fenchel-Rockefeller sentence. So to write it down like this. And we can use a trick to write the constraint set with help of an operator. So we can define, so the constraint set here, you can see it, or you can interpret this as having this as a function with respect to the equivalent martingale measures. Then this function has to be pointwise less or equal than a constant value, right? And this is something we can use so you can write down the constraint exactly in this case, where we now consider functions of or on the space of equivalent martingale measures. And we can equivalently write this constraint like this, having bound-wise or point-wise boundary. And so we can define now this to be our linear and continuous operator we need in the dual result. And yeah, we consider the space of bounded measurable functions on the set of equivalent martingale measures and have some sigma algebra. So this constraint is satisfied if and only if our newly defined operator is an element of L plus minus this constant term. So this helps us to get the primal problem in the form we want to have it. So we can write the constraint set as this indicator function. So the constraint is satisfied if our operator A times phi is an element of this cone.
So what's
S
S?
is a sigma algebra on the set of equivalent martingale measures, and it will be the power set, also the sigma algebra generated by the power sets. Okay. So we have now a problem that is of the form of our Frenchel duality theorem, and we can calculate the conjugate functions and adjoint operators to get the dual problem. But to get strong duality, we have to take care a little bit on which choice of topologies we have on the space. And yeah, because in general, if you endow the space of bounded measurable functions with a norm topology, you will get to the space of finitely additive measures. And this is something we cannot use here because we need Tonelli's theorem, so you get a little bit trouble. So we want to have a dual space of sigma additive signed measures, and this is why we will endow the space L with a Magai topology to get really the dual space of sigma additive measures. So this is something one has to take care a little bit of. And then also, this is a case where this regularization condition is too strong. So I was looking for some weaker condition that is satisfied. And for example, in the paper of Borwein and Shu from 2006, there is a a duality result with a little bit weaker regularization condition, and we really get strong duality between our problem and this dual problem. Okay, so this just as a short review of the proof. So we get for our randomized test the structural result being like a Neyman-Pearson test, and so this also helps us to get a result of the structure of the solution to the whole problem. So the structure of this inner problem now can also be applied for the whole problem. So we can show that there exists a pair Q tilde and a dual solution lambda tilde that solves now the total dual problem. And with help of this dual pair, we also get the structure of the solution to the whole problem, to the whole static problem. So we can show that so Q tilde and lambda tilde was a dual solution, and the phi tilde we can now define with help of this dual solution. So the density of the measure Q tilde and the dual solution lambda tilde, and we again get this typical 0-1 structure of the optimal randomized test. And we also get this condition, which means now really that the solution of the static problem gives you a modified claim for which the superhedging price of this modified claim is really attained by our capital boundary. So we use the whole amount, the maximal capital we have allowed to use. So we really use this whole capital. Okay, so this phi tilde defined in this way will be the solution to the static problem. And as you remember, the decomposition we saw at the beginning our capital boundary, together now with the super hedging strategy of this modified claim, will solve our dynamic problem. Okay, so what does it mean? It means that the solution which has this structure, we can multiply it to our original claim. We have to super hedge this modified claim and we get the risk minimal hedging strategy. And because of the 0-1 structure, this modified claim will be a kind of knockout option that is 0 on a certain value and has a value h on a certain set, and will also have a value in between 0 and h on the remaining set. Okay, so this is the main result, that to get the risk minimal hedging strategy, you will have first to solve the static problem and then find the super hedging strategy of this new modified claim. So as a summary, we also find that our solution to the static problem will have this typical 0-1 structure, which also appeared on, by the results from Vollmer and Leuker with the efficient and how was the other called? Quantile. Yeah, quantile hedging, okay. So quantile hedging, here it is. So this was the paper where they used the probability of the shortfall to be minimal, and the efficient hedging was a paper where they used the expected loss function. And in these two cases, it was possible to, at least for some specific loss functions, to apply the normal Neyman-Pearson lemma and to get this result. In our case, it was not possible to apply the Neyman-Pearson lemma directly. So we had to show with a duality result that we can switch the min-max into a max-min. And then we needed something like a generalized Neyman-Pearson lemma, which we got with help, again, of convex duality. So in our case, I applied 2 times the Fengel duality to solve the problem and to get the structure of the randomized test. So these results can be found in a paper of mine that will appear in Applied Mathematical Finance. And at the last point, I just want to give a little bit the overview, how it would look in general. So I already mentioned if we can write down the problem a little bit more general with the linear continuous operator A and random variable B here, and also in the constraint set, we can write down it in a general way such that as well the testing will be a special case, and also the convex or coherent hedging for some certain choices of risk measures. And so this was what we have just considered, the convex and coherent hedging case. You can also think of using like a robust version of efficient hedging, so to use the expectation of a loss function, but not only for one fixed measure, but you can take model uncertainty into account, so you can take the supremum of the expected loss as a risk measure. And you also come from this dynamic problem to a static problem, where the risk measure appears here again. And for some specific loss functions, you can apply the results as well and get this typical structure of the solution. And also, if you write down the problem as general as it is here on the board, the test problem, the testing of compound hypothesis is also like a special case. And as I already mentioned, in this case, the risk measure is now a coherent risk measure that has a dual representation with respect to the family of probability measures that appear in the alternative hypothesis. And the compound null hypothesis will appear in the constraint set, of course, where in the hedging case, equivalent Martingale measures appeared. Okay. Sorry? 10 minutes left, so what should I do? Maybe we can go. No, it's fine.
Okay, very
in the complete market, so if you use a capital that is a little bit less than the fair price, so you can still look at this problem, and in the complete market you can get more explicitly results. But still the problem is a little bit that so this representation depends on the dual solution. So this is in general very hard to get really to calculate something. Even if you take a concrete risk measure, like the average value at risk, so we already know how the set Q looks like, but it's still not so easy to get the optimal dual solution. So I've not yet got a real example where you can calculate the strategy. Also, the problem is that if you are in an incomplete market, to finding the super hedging strategy in general, it's like an existent result. So it's very hard to really explicitly get the super hedging strategy. If you're in a complete market, then this is not the problem. That's true.